Good morning. My name is Lai Wei. This summer I worked on integrated microwave ultrasound imaging system. My work involves heavily with MATLAB programming, so the goal is to build a programming tool to analyze acoustic data and reconstruct ultrasound images. My mentor is Professor Magdam, and I'm working with Mark Haynes. Here is a brief idea. I acquired time data from an ultrasound ring array designed for breast cancer imaging. I reconstruct an image of speed of sound from the data by using filtered backprojection. And before all that, I need to test the algorithm in simulation. So I first create the object by assigning speed of sound to each point in the object. I assume sound propagates in straight line and collect time of flight data over different paths. Then I filter backproject the time data to reconstruct the object. Here is the detailed procedure. So first I create the object. Here is how I did it. It's a 400 by 400 points matrix. It's a 2D object. So if we just choose a point, like this one, the x and y value of that point represents its 2D, its spatial location in 2D space, and the z value represents the speed at which the sound wave propagates through that point. And this is just the projection of the previous picture on the xy plane. And again, x and y value represent its spatial location, and the different color represent different speed of sound. And after we have the speed of sound data, we can place the transmitter and receivers in order to acquire time data. This one is a real experimental setup. On the ring, there are 256 transmitter receiver sites, and each transmitter transmits a sound wave to all the receivers, and the receiver acquires time data for that path that the sound wave propagates through. And the object is in the middle of the ring. And this is a configuration made by MATLAB. As you can see, each point represents the transmitter-receiver site, and the line between those points represents the path that the sound wave propagates through. And after we have the transmitter-receiver set, we can now acquire the time data, and here is how we did it. So this one shows from the first transmitter, it emits sound wave to all the receivers. And then from the second transmitter to all the receivers, from the third one to all the receivers, and so on. And the way the time data is stored is that the first row of the time data matrix contains the time of those paths that comes out from the first transmitter, and the second row of the matrix contains the time of those paths that comes out from the second transmitter, and so on. But this is not what we want. So we need to do interpolation. We need to do manipulation. And here is a reason to do manipulation on the time data. We have acquired data with a ring array of transmitters and receivers, but in order to apply filtered backprojection to reconstruct the object, we want the data to be collected for evenly spaced parallel beams at different angles. So as this one shows us, for those different paths, those different parallel paths, we collect the data, and then we rotate to a different angle, and then we collect data for different parallel paths. So we need to rearrange the data to get a parallel beam evenly spaced geometry. This is just a reminder of how we store our data. So the time of those paths from the first transmitter goes to the first row of the matrix, and then the second transmitter to the second row of the matrix, and so on. And then this is how we want. We want the time of those paths that makes a 0-degree angle with the y-axis goes to the first row of the matrix. And then the second row of the matrix contains the time of those paths that makes a 15-degree angle with the y-axis. And the third row, the fourth row, and so on. And as you can see that it contains all the data as the previous one. It's just it gets reallocated. Then we need to do one step further for the third one. We need to do interpolation in order to make each row of the matrix contain the time of those parallel paths that are evenly spaced for each specific angle. So after we manipulate the data, we can get the sinogram. The sinogram is formed by stacking the projections for all angles together. If we look at this, the y-axis shows different angles. So if we choose 100, every point on this line, the value of every point on this line means the time of those parallel paths that makes a 100-degree angle with the y-axis. And on the right is the filtered sinogram after ramp filtering. So after we have the sinogram, we can do backprojection. The idea of backprojection is to take the filtered sinogram value at a certain angle. In this case, it's phi, and then smear them back along corresponding paths. So this is one path. You smear it back. There should be some other paths, but I didn't show it. So there are some other parallel paths. You smear the data back, and then you rotate to a different angle, then superimpose them. So this is how the MATLAB did it. You can see it's kind of rotating. So the MATLAB do the back projection at each different angle and then superimpose them. And that's the final result. And here is a comparison between the original one and the reconstructed one. And as you can see, the only difference is that the resolution. So in order to increase the resolution, you need to increase the number of transmitter-receiver sites. So what else did I do? I also made a user interface for the user to create the object. So the user can specify different parameters like background, velocity, transmitter-receiver numbers, and the shape of the object. And in this case, it's a Gaussian distribution. And this is an image of object attenuation. So instead of representing the object with speed of sound, you can also represent the object with attenuation factor. And this shows my program works. So what makes my program different? MATLAB program online can only do there are some MATLAB program online that can do filtered backprojection, but they can only do it for evenly spaced parallel beam data. But my program deals with real data that are not evenly spaced and are not parallel. And the MATLAB programs online use ramp filter that is sampled in spatial frequency domain, which knows the DC component and needs actual work to restore it. But I used spatial domain sampled ramp filter that avoids aliasing and does not know the DC component. The filter work will be analyze real ultrasound data with my program, and then incorporate speed of sound images formed with filtered backprojection into full-wave inverse scattering image algorithms. The third one is to combine ultrasound and microwave data for better image reconstruction. Thank you for your time.